Now, the next two periodic trends I want to link together a little bit because they tend to get confused pretty often. And those are electronegativity, everybody's favorite 8-syllable word, and ionization energy. And we're going to do a little personification exercise. I feel guilty if I don't at least use my English background a little bit throughout the year. And we're going to talk about electronegativity as an element's desire to gain electrons. We'll even go one step further and call it a greediness for electrons. And since Halloween's a week away, and after that, it's pretty much Christmas season, we'll use Christmas characters to even take that personification to another level. And the most electronegative elements on the periodic table would be our Grinches. If you want, find the most electronegative, and that would be your Grinch. We know now that the staircase separates all the elements on the periodic table into two basic categories. We're not going to worry about the metalloids right now. And that's basically the nonmetals to the upper right, above and to the right of the staircase, and the metals below or to the left of the staircase, with the exception of hydrogen. Now, the nonmetals, as a general rule, tend to gain electrons in order to achieve their full octet. The reason being that most of the nonmetals have either 5, 6, or 7 valence electrons already, so they're close to that octet. The easiest way to get there, to achieve an octet, is to gain electrons, which means they end up with high electronegativities. Nonmetals are greedy. The metals, on the other hand, are our lovable losers. We said earlier, I have nothing against metals. I mean that strictly in terms of electrons. But the reason being that in order for them to achieve a full octet, since most of them have 1, 2, or 3 valence electrons, it's easier for them just to lose the valence electrons they have and go back down to a full octet in the shell that's below or inside their valence shell, which means they have low electronegativities. Not only do they not want other elements' valence electrons, they don't even want their own. So metals have very low electronegativities. They're not very greedy at all. I'm sure that you were hoping that I would use the teacher version of this so you'd have the answers, but no luck. Use Table S. Table S toward the back of your reference tables, the CRTs. Open it up. It's sort of like if elements had baseball cards, you'd be looking at it. Those are the stats for all the different elements. Now, the good news is you do have a hint already. The most electronegative elements we just said are going to be your nonmetals. Don't waste any time looking for metals there. You don't need to worry about it. And the least electronegative elements are the metals. So don't worry about looking at nonmetals for this one. And you should find that you have a tie. Talk about that a little bit later. Now let's talk about the trend. Going across a period, electronegativity increases. Why? Well, let's look at the same two factors we've been looking at all along. Nuclear charge increases. That means we've already said the effect of an increased nuclear charge is to pull the electrons in more tightly. Shielding does not increase. Shielding does not increase, but nuclear charge does. So nuclear charge is fighting nothing. For that reason, electrons get pulled in more tightly, and that also means that as the nuclear charge increases, an element has a greater tendency to attract other elements' electrons. That's where your electronegativity increase comes in. Okay, a greater nuclear charge with no increased shielding means an element is going to pull harder on other elements' valence electrons. Great thing about this period is that there are no transition metals. There's nothing to buck the trend. Perfect. It shows very clearly that as you move from sodium to chlorine, electronegativity steadily rises. And again, that's because of increased nuclear charge and no increase in shielding. Now, down a group, you have an increase in shielding, and we said we're not even going to bother writing down that nuclear charge increases because it doesn't matter. Increased shielding trumps that, which means electronegativity decreases. If you increase shielding, here's your nucleus for helium, right? There's nothing between this nucleus and the valence electrons. Now, if you look, here's your nucleus for neon. You've got these two valence electrons, or two kernel electrons, shielding the nucleus from the valence electrons. Argon has 10 kernel electrons doing the shielding. So we already said that means that when you increase shielding, an element holds on to its electrons less tightly. Well, that also means it's going to have much less pull on another element's electrons. So as you move down a group, that increased shielding means the elements will have a lower electronegativity and be less greedy for other elements' electrons. Now, ionization energy. We're going to stick with this personification exercise. We said if electronegativity is greedy or greediness, ionization energy is stinginess. And sticking with our Christmas theme, who's the stingiest character of all? Scrooge. People often make the mistake of assuming that ionization energy and electronegativity are opposites, and they are not. Ionization energy, really from this long definition, what you need to take out of it is the energy to remove an electron. All the gas phase and most loosely bound stuff, it's blah, 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 blah. What you need to know is it is the energy required to remove an electron. Stinginess, that means how tightly you're hanging on to what you already have. Greediness, how much do you want what other people have? Stingy, how tightly do you hang on to what you have? We're going to use that analogy here for ionization energy. We're going to build on what we did with electronegativity. Now, as you move across a period, nuclear charge goes up, shielding doesn't. Well, if nuclear charge increases, that means the positive charge is going up at the core. The elements are going to hold on to their valence electrons more tightly. There's no increased shielding to screen the protons from the valence electrons. So across a period, ionization energy increases because nuclear charge increases. And you'll look, there's some questions about, this is a great little graph. It looks like a stock market. And again, that illustrates, we said these are trends as you move across periods. And each of these, as you see here, marks the start of a new trend. Now going down a group, we say if shielding increases, we don't even worry about nuclear charge. Because of the increased shielding, we already mentioned, the effect that has is that the protons have less pull. They pull with less force on the electrons they have. That means it's going to require less energy to remove electrons as you add, helium has no shielding, neon has 2 shielding electrons. Again, we said argon has 10 shielding electrons. It's easier to get valence electrons away from argon than it is from helium because the protons that are trying to hold those electrons in place are screened by a lot more electrons. There's a lot more shielding from the kernel electrons in argon than there is in neon, and there's no shielding in helium. And our last topic, our last periodic trend is reactivity. This one, for my money, tends to be the toughest. And that's because you have to break up the periodic table into its 2 types of elements again, the metals and nonmetals, and you can't compare them to one another at all. This is the tendency to react with other elements. Well, here's the deal. Metals, we said, are losers when it comes to electrons, and the nonmetals are bullies. Metals are trying to get rid of their electrons. Nonmetals are trying to take other elements' electrons. And, of course, I can't resist a really bad pun. But because of the fact that metals are losers and want to get rid of electrons and nonmetals want to gain, you can't compare nonmetals to metals. You compare metals to other metals. You compare nonmetals to other nonmetals. Okay, so for the metals, we said the most active metal is francium. Find francium. It's in the very bottom left-hand corner of the periodic table. So as you move across a period from left to right, you move away from francium and cesium. So it should be logical metal reactivity decreases. You think about it. You guys commonly think of copper, iron, silver, lead, gold as your common metals. Well, they are not reactive metals. That's a good thing. That's why they're used for cookware and for jewelry and to build cars and other stuff. So as you move across a period, metal reactivity decreases. Why? Remember, metals want to lose electrons. Well, you've got increased nuclear charge. That doesn't work well with elements that want to lose electrons because it makes them hold on to the electrons more tightly, and shielding doesn't increase. That also doesn't help metals react. So you're increasing the pull, the positive pull toward the center, and you're not increasing shielding. So metal reactivity decreases going across a period, down a group, it increases. Why? We ignore the fact that nuclear charge increases because shielding trumps it. And since shielding increases, that means it's easier to lose electrons. They're shielded from the positive protons. Then we look at the nonmetals, and this video is, I think I've already shown it to you, but if you haven't seen it, it's group 1 metals reacting with water. It's worth the 4 or 5 minutes. Nonmetals, on the other hand, we said these guys want to gain electrons. The most active, the Grinch is fluorine. Going across a period, reactivity increases. All right? Reactivity increases across a period. Why is that? Well, it's because of increased nuclear charge and the fact that shielding doesn't increase. So adding positive protons, again, pulls things in more tightly. So it means not only are you going to pull in, does fluorine pull on its own electrons more tightly, but that increased positive charge in there pulls on other elements' valence electrons. Now, the exception to this is the noble gases. They're unreactive or inert. Why is that? The way we're going to describe this right now is they already have a full octet. 8 is great. They have 8. Since they have 8 already, they're not trying to gain any more or lose any electrons at all. They want to stay exactly where they are. That makes them inert, inactive, unreactive, however you want to call it, and that's why they're called the noble gases. They don't bother anybody. And then we talk about going down a group. Going down a group, reactivity decreases for the nonmetals. Why is that? Because one factor, increased shielding means, again, nonmetals want to gain electrons, and when you increase shielding, you have less hold on your own electrons, and that means you also have less ability to pull from other elements' electrons.